Energy efficiency in railways has been increasing in the last years, thanks to a number of factors such as improved components or subsystems and new deployed technologies. Unfortunately, this type of costly mechanisms cannot provide further and significant reductions, although we believe that electric railways have still a great potential for further improvements in efficiency. On top of that, minor changes in the baseline scenario, for example new vehicles, fluctuating price of energy, different timetables, will have for sure a big impact in the optimal solution. The goal of reducing energy consumption locally may not be the best one from a system point of view, because of a number of cross and side effects. This is the environment where MERLIN project was conceived and launched 3 years ago. MERLIN was co-funded by the European Commission under the FP7 program and coordinated by UNIFE, and it gathered more than 20 partners coming from the rail industry, infra managers, railway operators and research centers from all across Europe. The ultimate goal of the project was to investigate and demonstrate the viability of an integrated optimization in order to achieve a more sustainable and intelligent management of energy in the electric railway systems in Europe. In that sense, the project has addressed the integrated energy management in several traffic scenarios. For example, high speed, freight, regional, commuter, and mixed freight passenger. MERLIN relied on an integrated optimization approach that includes multiple agents, dynamic forecasting supply-demand scenarios, and cost considerations, and all of these in order to support the strategic and operational decisions. Once implemented, the MERLIN solutions, some of which were tested along the 3 years of the project, will enable an overall reduction in energy consumption at system level of 10% by 2020.
French Railways wish to increase the capacity of high-speed line 1, which is between Paris and Lyon. And one of the difficulties is that the public power system is weak between the crossing of the Morvanville, which are roughly halfway between Paris and Lyon, and that it's not reasonable to build a new substation where the increase of capacity will need. We wish to increase the capacity of the line from 13 trains per hour till 16 trains per hour. This is to say that an increase of roughly 3 trains per hour. We hope that better management of the energy available will allow this increase of capacity. A better management is first to use substation with a storage system. The substation will store the energy during the night and reuse the energy stored during peak hours. And the second track is that better use of the energy available by monitoring of the speed of the train that will smooth the use of energy. So this is the problem that we address to MERLIN.
The first solution is a software solution which aims to shift a complete timetable of trains in one direction in order to avoid accelerating of different trains at the same time. This aims at reducing power peaks and power reduction at substation levels. The second solution is also a traffic management solution using an ATS, automatic train supervision system, which solves conflicts between trains, for example, avoiding braking, stopping and accelerating. There is significant benefits when we avoid a train to stop. The third solution is a hardware solution with the modification of existing substation, adding alternative energy sources like renewables or adding energy storage system. For example, when we store energy during the night, we can re-inject it into the railway power system in order to reduce power consumption during rush hours. Finally, the three solutions can be combined in order to minimize the energy consumption and reduce power peaks, and then increasing the line capacity.
We are looking at two different problems in Merlin. The first one is about minimizing losses in the rail power grid. We are examining a line between Malmö and Alvesta in southern Sweden. It's a double-track line with quite heavy traffic, daytime mainly passenger traffic, and during night freight traffic. There are 3 converter stations on the line, and we are seeing that these converter stations not just are feeding the trains near the station, but also over longer distances. And this causes losses and energy costs money. So by changing converter parameters, we hope that it should be possible to minimize the losses, and that will be done by simulation by Siemens. The other line we will look at is from Malmö to Simrishamn with a converter station in Ystad. And this is a single-track line with quite heavy suburban traffic. EMUs used on the line have quite high installed power, so we get very high power peaks. But these power peaks are just a couple of seconds long, and their idea is if it is possible to shift these power peaks, like just a few seconds earlier or later, we can maybe reduce the peaks by 30% or so without affecting the timetable. And then this way we are hoping that we can lower our investment costs. And also this will be done by simulation, and there we will see if it is possible to do that without affecting the trains.
Our task was to study the 2 cases. The first case regarding energy efficiency, with the task to reduce the losses by adapting the converter parameters. To be able to do this, we developed a converter model which has been used and in our simulation tool CityTrack, and also did an iterative process to optimize parameters with the tools which have been developed in Merlin. So for the first study object with the reducing energy in the system looks quite convincing, so we optimize parameters, but are still in the progress to find how much we could reduce the power. But it tends in the right direction, that the energy in the system could be optimized by this method. For the second task, where we should look if we could reduce the power peaks of the system, we had 2 approaches. One approach was to modify, let's say, the train starts, the departure time of the trains, and the second was to alter the driving profile of the trains, taking into account not to shift the timetable. We already have preliminary results. Power peaks in the substation could be reduced by approximately 20%. The conclusion, both targets could be reached by optimizing the converter parameters. The energy flow in the system can be optimized, and also the energy demand could be reduced, so losses could be reduced. And the second subject looks very promising, and I think that it is demonstrated quite well that only short modifications in the timetable can reduce the power peaks, and then the goal of traffic record can be reached by that.
The Spanish scenario is formed by 2 different lines. First line, between Malaga and Fuengirola, is a 30 km length line with single and double track to suburban traffic. The line is fed by 3 electrical substations. The trains, type Civia is 464, circulate in a single composition with frequencies of 20 minutes. The first line has 18 stations along of 30 km, so trains must stop several times during the journey. As a result, 2 problems in normal at the grade's operation arise. On the one hand, a great possibility to recover braking energy. The problem is that many sections of the lines are single track and the frequency of train is low. The direct consequence of this is that the energy is not used and must be burned.
This line has both single and double tracks. Single tracks means complicated operation because all trains have to be synchronized. Being or not being synchronized has an important effect on the energy consumption.
Other common problems are the producer peaks of consumption during the starting of the degraded operation. therefore to have some terms of contracted power very high and also at a high cost. Therefore, it is necessary to analyze the possibility of placing a storage system in order to reduce, even in degraded condition, those peak loads and also to know the most efficient use of the recovered energy. Other important issue to analyze is the possibility of minimizing the terms of contracted power to reduce cost. That means a direct saving in the energy bill.
MERLIN provides us two relevant tools to solve the issues and fulfill the needs of the suburban scenario of Malaga, namely a strategic decision-making tool and the REMES, the Railway Energy Management System. From the strategic point of view, it was determined that the deployment of energy storage systems could help to reduce the energy consumption, power peaks, and even the contracted power. The strategic decision-making tool was run to find the best combination of a number of design factors, like the energy storage capacity, its location, and the cost, to obtain the optimal results. From the operational point of view, the solution relies on the REMES. In other words, it relies on the deployment of the rail smart grid proposed by MERLIN. In this case, CAF, supported by ADIF, Renfe, and Saldo STS and the University of Aachen, implemented a real pilot case in the suburban network around the city of Malaga in Spain. Two of the REMES components were implemented and installed. First, the local optimization system, LOS, governing the area between Malaga and Fuengirola. And second, the Dynamic Onboard Energy Manager, DOEM, mounted on a Sevilla train, being both connected through the public 3G network. The test lasted for 2 weeks and proved the feasibility of the REMES concept and the MERLIN's reference architecture. The whole system saw its resilience to the degraded modes, changing the behavior of the agents to fulfill the timetable and the power contract. To sum up, MERLIN has provided a set of solutions for the suburban scenario in Malaga, thanks to its powerful tools, achieving better results than expected in both simulations and real tests.
The West Coast Main Line is one of the busiest mixed-use traffic lines in Europe. We've got 43% of the UK's rail freight uses the line, and we wished in REO4 to focus on a line in the north of England, on the north end of the route. One of the biggest problems that we face is that whilst lines are being upgraded, there are electrical constraints which limit the number of electrical trains that can operate on a given route or section of line. So what we'd like this scenario to do is look at how, given a particular service pattern, we can best utilise the mixture of diesel and electric services on the line to give us the best energy consumption.
Scenario 4 deals with the West Coast Main Line, and the objective is to find a strategic decision onto what is the trade-off between using electrical traction or diesel traction. This will be with the objective to minimize both electrical consumption and diesel consumption within the network, and therefore optimizing the energy consumption. For this purpose, we used a newly developed tool specifically for this project called the Strategic Decision-Making Tool, SDMT, which takes advantages of the existing railway simulation tools like the one provided by Network Rail called Vision Oslo. We looked into the timetable and trying to identify of all services which of these could be actually potentially using either diesel or electrical traction. We focus on the freight services, which are the only ones that could do this, and we identify 19 of those. Once we plot all the results into the graph, we obtain this Pareto front optimum graph, and that will give you all the necessary information to make an informed decision about the trade-off between electrical traction or diesel traction in these particular services. As an example, we picked some random points on the graph and we looked into the meaning behind all the data there. And we found, for instance, there was a particular combination of 10 diesel services and 9 electrical services that will give us a lower energy consumption. These results give you proof that we can actually use these sort of strategic tools to make decisions that will allow optimizing energy consumption in a long-term perspective.
Scenario 5 looks at a section of the line in the south of England where we have a large network of 750 volts DC electrified lines which run via a ground-mounted third rail. One of the key questions that we'd like to answer is whether we can optimise, given the space constraints that we have on our network, the location of a substation and its no-load voltage during a renewal. And what we'd also like to do is then look at whether a REMS could be useful to us in the future to optimise the energy consumption for given trains during periods of a disturbance such as a circuit breaker outage.
Unsolved STS within the scenario 5 has performed a lot of simulations using the SDMT and REM tools. We are now very close to the end in order to find the best solution for one railway's lines with the positioning of the substation and the voltage, no-load voltage of the substation itself.
After 3.5 years of hard work, MERLIN has come out with 3 main achievements. The first main achievement is the development of the reference architecture of our proposed railway smart grid concept, namely REMS, including its functions, interfaces, components and protocols, following the Senelec ETSI SGAM model. To serve as a basis for the energy management systems in the railway domain, we have combined the technical developments with new business models to enable and foster their application. The second main achievement of the project is a strategic decision-making tool based on MERLIN's architecture to support the design of the rail smart grid. The tool takes into account the business constraints and suggests modifications for the system layout after analyzing, by simulation, the scenario during a complete running cycle. This closes the loop, allowing MERLIN to become a comprehensive solution for the implementation of an interoperable rail smart grid. In that sense, the proposed architecture and tools have been evaluated in the high-speed, freight, regional, commuter and mixed freight passenger traffic scenarios. Significant improvements in subcontracted power, consumed energy and cost have been obtained in most cases. MERLIN's third main achievement is a pilot case of this integrated approach that has been deployed in the suburban network of the city of Malaga for its evaluation and assessment, obtaining good results. The deployed components show the potentials of MERLIN's concept and the real operational conditions. Last but not least, MERLIN has issued a number of technical recommendations and implementation guidelines to facilitate the market uptake of the project concepts and results. To sum up, MERLIN has pioneered the holistic management of energy in railways. This opens the door for further studies and a system-level demonstrator within future initiatives like Shift to Rail.